professor of geology at the University of Utah. A fervent author, written over 100 papers, many national awards, distinguished international lecturer, and we quizzed her last night where she gave 53 lectures in 6 countries in this recent 2011 year sequence with her 2014. She's a graduate of the University of Wisconsin, where she did her PhD. She was, and I've known Margie for something like 35 years when she came to Utah. She did a 7-year stint as department chairman at Utah, and really was the person who helped design that beautiful building we're in. She made the major, I would say, academic design of how the systems work together and how the experiential ideas throughout the building came together. She's, as I said, she's earned numerous awards. In the last 20 years or so, she's gotten into the Mars ideas. If you saw her talk last night, you see this marvelous distribution of work and photographs of technology applied to Mars and the correlatives on down here on Earth. So I just want to thank her once more for coming up, and we're trying to get some clearing of the fog this morning so she can see that the Tetons truly are here. And I invite you all to talk to Margie afterwards, and thank you, Margie, for coming up.
Thanks. We need to turn down.
Yes, I'll take care of that.
So I'm going to do something a little bit different today, and we can be kind of casual since there's just a few of us here. But I wanted to talk about some hot topics that I think exist in the field of sedimentary geology. So there's a little bit of a buzz, so it shakes every once in a while, but hopefully it won't be too bad. So I'm going to talk about 3 things. First, I'm going to talk about the philosophical ideas that we have about the stratigraphic record and some of the approaches we're using. And then secondly, I want to actually be informal and discuss some puzzles in sedimentary geology. And I'm going to show you pictures and then see what your response is, what your interpretations are. And then third, I'm going to talk a little bit more in detail about some of the types of things that are happening in the future using cyber technology. So first of all, with philosophical questions, it's really challenging being a sedimentary geologist because it's like Swiss cheese. We get to see these little pockets, these little windows, and what we're trying to do is reconstruct everything around that. What is the framework of the geologic record? Come on in, no problem. And we have these certain paradigms. We're taught that the present is the key to the past. But there's a lot of things in the past that don't really have good analogs. We are also, oh boy, that was really getting there. There's more gaps than records. So actually, if you look at the stratigraphic record, there might be more time at an unconformity. There might be 10 million years missing at an unconformity, whereas the amount of record that you see might represent maybe thousands of years, maybe tens of thousands of years. So there's sort of an imbalance there. We don't know if sedimentation is continuously happening or what's normal. I kind of feel like I'm drinking a cup of coffee. I don't drink coffee, but again, he's doing that. And sometimes maybe not everything gets preserved in the record. Maybe even some things are biased because big events have more likelihood of being preserved than normal everyday events. So all of this is kind of challenging when we're interpreting the stratigraphic record. But we're getting better, and different things are helping us, so we're doing more detailed field work. Even sequence stratigraphy was a big change in how we view the stratigraphic record and our ability to actually predict things in vertical sequences as well as what might be happening laterally. Other things that I'm sure many of you were involved in are aspects of modeling. So basin modeling and visualization has really helped our interpretations. And there's lots of things that we can do to better understand things in the subsurface and make better risk assessments and analysis. Other things that are helping us understand processes would be flume studies, modern studies of what happens when we have certain sediment and we run that through a flume. We can look at velocities. We can look at what bed forms will happen. We can look at what happens when we change certain parameters. So we have not only water flumes, but there are also wind flumes. And all of those are helping us understand some of the mechanics of sediment transport. And then some of the other things that are happening are we're getting improved instrumentation. So this is a QuemScan instrument that we have in our department. This allows you to actually do very detailed analyses of compositions. So in the old days, we used to point count with the petrographic scope. And we might have to count 800 points or something like that. But now these machines can do a lot of that work for you. You just assign value. You say this particular composition is going to be this grain. How many of those grains do I have in this slide? And it'll tell you. Volumetrically, it'll give you a number. So that is changing how we do things. And of course, there are more and more isotopic approaches that are helping us in many analyses. But really at the core of the geologist, and that's really what I'm kind of focusing on today, is careful observations. And I think of geologists as being detectives, where we're trying to look for clues to try to interpret what might have happened at the scene of the crime, but it might have been, 100 million years ago or something like that. And so this idea of the Sherlock Holmes, how are we using evidence to make interpretations? And even one famous sedimentary geologist, Ray Murray, who wrote a classic textbook, Origin of Sedimentary Rocks, Black, Middleton, and Murray, he became very involved in criminal investigations, and this is known as forensic geology, and this is where he could use different things, different techniques that we use as geologists to make observations and actually help solve crimes based on some of these kinds of observations. So to go along with this, I think one of the interesting ideas was when one of our alum, Jack Schroeder, who was at Nebraska, he actually saw these pictures of Osama bin Laden after 9/11, and he was able to say, I think I know where he is, based on the outcrops that were in the background. And that's kind of amazing when you think geologists are absorbing all this information and they're able to actually make some interpretations out of even scanty photos to try to tell take these clues to tell where this guy is. So that was something that made quite a bit of news, and people were amazed that a geologist could actually tell where Osama bin Laden was in this image, even though there was all this higher intelligence that was trying to figure out the movements, etc. So what I thought we could do is actually try to apply some of these observational skills into some examples. And so I'm going to have 3 examples, these A, B, C. And I'm going to kind of start with a small scale example and then work our way up to a big example. So this is where you can try your skills of observation. So here we are at an outcrop in Santa Fe. And this has been mapped as the Miocene Tasuki Formation. And this is a quartzite. And it is an incredibly hard quartzite. And I'm used to hacking soft rocks, but I can swing a hammer pretty well because I have a low center of gravity, being short. And I try hitting this rock, and it is really tough. And it just bounces right off. And even most quartzites aren't as hard as this one is. And as looking at this, this part right here was really highly polished. So this is a quartz arenite, but it's quartz cemented. And this part's really polished. Now, why is this part polished right here? So,
Indians sat on it forever.
Indians sat on it forever? And what gives you that clue? What made
It
that?
looks like a great place to sit down.
Yeah, it does. But wouldn't they sit up here where it's a little flatter? This is probably pretty hard. I mean, I would slide off if I were sitting there. But you made a very good interpretation, and maybe something that you didn't. I'm not sure if you noticed it, but this right here. You see what that is?
That's petroglyph.
It's a petroglyph right there.
No, there it is.
So you did make that connection to natives. And I kind of wondered about that. What are some of the other possibilities?
Glacier.
I think it's where a cow rubbed her butt.
Ah, okay, that could have been possible, although this is in a subdivision. I don't know if you can see the road behind there.
Yeah.
I don't think there's a lot of cows going there now, but maybe in the past, could there have been something like a glacial polish? Well, it seems odd that this part right here is polished, but not a lot of the other stuff around it's very polished.
It looks like something is spalled off right there.
Yeah, because it looks so smooth right here.
Well, and the lip down along the bottom, looks
Down
like
here?
yeah,
right here?
right there.
Kind of flake, yeah. So, my students have said, could it be aeolian, blasting? Could there be wind erosion that's kind of almost like a vent effect gets polished? Could that be it? But I don't know, it just seems like there would have been other places. Why just
Yep.
this one
Right
spot here? And I actually thought maybe a native was actually kind of rubbing their arm across here as they were working on that petroglyph. But there were petroglyphs other places, and it didn't seem to happen. So, okay, let me show you some other pictures. So in this same area, some of the same kinds of outcrops that are nearby are showing these kinds of structures. They look a little bit like sedimentary structures, and you can see them here. It's got kind of a lip here, steps down, lip here, steps down, and these are kind of curved. So if you were out in the field, what would you think about those?
Just thinly bedded sand.
Thinly bedded, but it seems odd that they're actually kind of stepping down this way. And even like in cross-bedded sands, it's usually not so smooth.
The edge of a lake dried up gradually.
Lake deposits, possibly. I actually thought it sort of looked, let me show you one more picture. Here's another one. It, to me, almost looked a little bit like a tufa, or sort of like a spring deposit. But these are quartz aaronites, they're not limestones. So one of the things here is that there's still mysteries out there, things that we don't know. We stumble across these things and we're scratching our heads, trying to figure out how we're going to put this into the story based on what we know. And these actually seem to be kind of curved surfaces, and it almost seems to be kind of mimicking some kind of topography. And here's another example.
Same place?
Same place. And they're not like ripples, because ripples are this regular repeating structure, and they're not so curvy like this. So this was a real mystery. One person said, could they be lode structures, and this whole rock has been turned upside down, and we're looking at the bottom of it. Well, this stuff is just so heavy. It's just really hard to imagine a large outcrop area getting turned upside down. So that didn't seem to work.
You said it's a quartzite. Is that a
Yes.
quartzite because it has been very deep, or because of the cement that's been injected in it later?
Even without the cement, it'd be a quartz aeronite. It's all quartz sand. There's some feldspathic components.
Not any
in there.
recrystallization at all?
I don't think so. I think it's
Okay.
just cement. I didn't include the thin section here. But here's another picture. Here's the outcrop. It's actually in the middle of a subdivision. This actually has lots of petroglyphs on it. And this whole surface that's kind of bumpy here, all of this is covered with those kind of weird structures. So this is kind of puzzling. And I'm not sure that I know exactly what it is, but the interpretation is difficult. So this is a mystery. And I think that it could be quartz cement that's actually coming, and in the subsurface, waters are oozing out of that fault and actually preferentially cementing some of these areas, but it has this kind of coliform looking texture. That's the best I've been able to come up with so far. And one of my colleagues who also looks at cementation from faults also thinks that that's probably the best explanation. But there are always these kinds of little things that are nagging. They're just not quite what we think they ought to be, and it's difficult to figure out an interpretation. Okay, now we're going to go to Chile, here in the Atacama Desert, one of the driest places on Earth. So this is kind of stepping up in scale. And here we've got a bunch of big boulders, and there's not much rainfall here. But one of the things about these boulders is that they're fairly smooth on the sides. And this is the work of Jay Quaid, who was also one of our alum. Took classes from me when I first started at Utah. He's currently at University of Arizona, Tucson. And I thought this was just a really neat study that he had done. And he showed me these pictures of these big boulders, but they're all smooth on the sides. And so I'm going to show you some pictures. Here's an example of this. So we look at these things and we try to take in information and try to take clues. You see these big boulders, they're kind of polished on the sides like this. But this is a landscape where there's been very little rain or water for a long time.
What about wind?
Giant bed of
Wind.
ice.
Okay, good. Wind is another thing that we came up with. And wind, could it be sandblasting this? But why not any of the top part?
Earthquake.
Okay, let's come back to that, Bob.
If you had a low ground velocity wind, you might get it on the sides and not on the top.
Yeah, if it's just staying down
Yeah,
low.
yeah.
And we do know that, let's say, sand grains tend to saltate only about a meter or so.
Right.
So maybe that's a possibility. John, did you have another thing you said?
Well, I'd said that fact, but if there's differential cementation, the upper part could differentially erode out.
Yeah.
That would be a first look at that, say the upper part's not quite as well cemented as the lower part is.
Yeah. It's not a distinct boundary. It's sort of indistinct in a way, though, for Betty. Yeah. I mean, we have to go through this whole process. Yes.
A leftover from an ancient ocean.
Leftover from ancient ocean. That's a possibility, although it's a long ways, and this is really up high. So it would have had to have been lifted up. Even though this is a subduction zone off to the side. I'll show you some other pictures to see if they help. Here's other boulders. You can actually see again that they're fairly smooth here. Here's another one. And in fact, the geometry is fairly close fitting here. But it's smooth on this side. Here's a carve or scale. So this is a big boulder field, and Jay was telling me this story and asking me what I thought, and I said, well, this is kind of confusing because it's not like there's no river system where you can see channels and these things would have been moved around by rivers, and there's nothing in here that seems to indicate that water was there. You know, water would leave channels or some other types of things on the landscape. And so Jay said he'd been out there doing some work, and he wasn't feeling very good, and he was lying down under the car, and that's when they were actually going by this boulder field, and he wasn't feeling good. He laid down under the car, and he was kind of looking up, and 'cause I think he was laying down there for shade, but he looked up, and he started seeing how these boulders were all smooth on the sides. And he was thinking about that, but he never paid that much attention to this boulder field before. And he thought he had an idea of how they formed, but he never quite had the evidence. But one time he came back to this area, and he was standing on one of the boulders, and he was going to try to date some of the boulders to see how old they were. And what happened was he was standing on one of the boulders, and all of a sudden there was an earthquake. As Bob said. And he said there was this earthquake, and the rock he was on started moving around, and he heard all this chatter, all the rocks knocking against each other. And he said there were all these clouds of smoke, kind of dust, really, that were actually kind of coming up. And the dust actually lasted for quite a while, even after the earthquake, strong ground motion stopped. And I said, didn't you get any pictures while you were there and this was going on? He said, Margie, I was just trying to I was like surfing this rock trying to make sure I didn't fall in between one of the cracks and get, stuck between these chattering boulders. And I said, oh, it would have been so good if you'd gotten a picture. But that was what gave him the idea that it was earthquakes that was actually causing this polish on the sides of the rocks. So these would be knocking against each other, and all this knocking over a long period of time would actually give this very smooth surface and account for the way the rocks would kind of nestle in against each other. So he actually was able to date some of these boulders to see when they were exposed, and he could estimate that there was about one earthquake every 4 months, because this is a subduction zone off of Chile, so it's fairly active. And he could actually calculate that based on the cosmogenic ages of the surface exposure of about 1 to 2 million years, he could estimate that these boulders have undergone about 50,000 to 100,000 hours of abrasion, and that's what's making them so smooth. So I thought that was just really a neat story, because it's not the one that we would normally think of. And it's just sometimes serendipity of science. He happened to be there, saw it actually happening, and then he could use some of his techniques of dating to actually get an idea of what kinds of processes are going on and even what the scale of the timing is. So I thought that was a neat story, and he was saying that maybe these things could even be applied to some of the lunar boulder fields on the moon. You see these boulders on the moon, and do they have polishing, or do they have abrasion that's going on? So this is again another idea of taking what we see in the geologic record here on Earth and applying it to other planetary bodies. Okay, this is our third mystery, and this is one in North Carolina. And this is kind of stepping up in scale. So we looked at little outcrop, and we looked at big boulders in the field, and now we're looking at something that's fairly large. You can see a road that's kind of going through here. And have people heard about the enigmatic Carolina bays? Nobody's heard about it? Okay, good. That's the way we want it. And that's what makes it more fun if it's a VSP you haven't already heard about. So there oftentimes are contributions that are made by people that are not necessarily trained geologists. And this one person, Michael Tobias, actually kind of brought the idea of these Carolina bays back to the forefront by some of these pictures that he did with using LiDAR DEM, the digital elevation models, and applying color to accentuate some of these bays. So I'm going to show you pictures of these bays, and we're going to try to make some interpretations of what they might mean.
When you say bays, are we actually looking through water here?
I'm going to show you that.
Okay.
Yeah, these are very shallow areas. Here's an area in Rex, North Carolina. This is an aerial photo, and these are some of the agricultural fields that are these blocks here. And sometimes they call these things grady ponds or citronella ponds. And they might have shallow amounts of water. Not all of them have water. Some of them do. As you can imagine, why they get the name citronella is because these are attractive places, I think, for mosquitoes. And one of the striking things about these is how they're aligned. So here's the picture again. You can see these river drainages, these river drainage patterns. So it does give you an idea about the scale of these ponds, and you get some idea of what the timing is based on these drainage patterns. So which came first, the ponds or the rivers? River cutting.
Rivers are cut into the.
It looks like the rivers are cut into the landscape that had these ponds. So this is again another clue that we're using to put together these stories. And you look at all these ponds, and look at how strongly aligned they are.
Glacial ponds.
Could they be glacial ponds? Problem is that this is an area, down in the Carolinas. The glaciated areas were way up north.
So
This area wasn't believed to be glaciated. Let's look at some more pictures. Here's another one showing a comparison. You can see some of the housing tracts. You can see the orientation of these. He actually took the long axes and tried to plot them up. And here you can see it with this image. They're the same photo, but just different versions. So they're pretty big. And here's an aerial image of one. You can see how the vegetation is concentrated here. It almost looks like there's these kind of raised ridges around the sides. And even back in, I think it was some of these photos, it looks like this is raised. Some of these areas are actually raised around the edges. And in fact, it even looks like there's more of a raised area right at the southeasternmost kind of ends of these. You might be able to see these in another picture. Here's another one where some of the growth is around these, but you can see some of the remnants of them here.
What kind of rocks underneath the soil? Is it limestone or what is it?
These would be coastal sediments. I think, I'm trying to remember exactly, I think they're clastics. They're not limestones like you would have down in Florida.
Right.
Yeah.
And it's interesting that if thinking structurally, it's like they've all been deformed along the same axis.
Uh-huh.
Which implies something moving.
Which gives you the sense maybe it's really soft sediment deformation, it's a mud flat somehow, I don't know.
Yeah. It's really kind of surprising that more of us haven't heard of these, because these are pretty big. So you've gotten to the point that I wanted you to do, which is to try to figure out what kind of explanation are we as geologists going to come up with to explain these things. What evidence do you think we look for, and what methods would we use to try to figure out what they are, and what do we think would be the most convincing evidence? What would be the smoking gun?
Asteroids.
So, what's that?
I just said asteroids hitting the earth in little puddles. I don't know.
Yeah, possibly making puddles. There'd be a big spray.
Is the grain size different of the sediments in the circle?
These are
compared to outside
actually,
of the soil?
they actually find that these are in sand, and it seems to be the same, this seems to be the same grain size as this. That it was made in these sandy deposits.
If you go back to your black and white image a couple back,
This one?
no,
Or
a little
back?
more, there. You notice there almost seems to be a white point, more or less in the center of many of them.
Yeah,
Like
I'm
right
not-
there.
Yeah.
Should we be thinking that is real, or is that just a bad
Yeah,
image?
I am not positive if that was something he added on to these
Okay,
images to try to just see what was the center of it.
okay.
Could they have been left by an ocean receding?
Yeah, this is a coastal plain area. But even if the ocean was there and then receded, why would it leave these kind of circles? Because we don't see these other places.
Well, it would have to be an asteroid coming at an angle, otherwise it would be circular.
Uh-huh.
And they're elliptical, so
Uh-huh.
if you had it coming in at this angle and blowing up, shredding,
Yeah.
then you would get these elliptical patterns.
Okay.
There would be a big change in the rocks if there was an asteroid.
Yeah.
They'd be fused and things like that.
Yeah.
What do you think the lineaments are in that image?
The lineaments?
Well, there's these things here.
Yes, ma'am.
I am not positive because I'm not sure that he explained that.
They look like they line up with the edge of the fields. though.
Yeah, they
Maybe
do.
roads.
Yeah, they might be agricultural things that are going on.
Well, the stuff
Not
along,
positive.
the stuff along the bottom of the image that's kind of horizontal with the bottom of the image
This here?
kind of looks like coastal
Dunes.
sedimentation
Yeah.
stuff. But then you see this cross-cutting relationship in there, and you kind of wonder,
Like right across here.
right, what on earth is going
Yeah.
on there? Is
Not positive.
Those are Indian mounds. Mary.
The depressions.
This is a tough thing, and probably what most people would come up with is, number one, is there something structural? Some structural grain in the bedrock or something that's causing that. A lot of people often say, could it be karst? But even karst topography that makes depressions is usually not aligned like this. They're usually kind of irregular things. And you have to have that limestone bedrock underneath.
Bedrock's how far down here?
I don't know exactly.
Could be way down.
Can you date them?
That's a good question. Maybe that is one of the things that we would try to figure out. How would we date them? If we're saying what evidence would we look for, and what kinds of things would we do? People have tried to date these.
Is there a lot of salt there? Like, could there be like
Not necessarily.
salt features
there?
Not there. Yeah.
do you have any idea what the dominant wind direction is?
That's another good question. Is there a dominant wind direction?
Because I'm trying to figure out how you get
West
this
east.
Uh
consistent ellipsoid.
huh. Uh huh. Some people have said that they think it could be related to winds, but I think one of the problems that I have with that is that winds are so highly variable, and why would it just be so dominantly one direction?
So the elongate axis is the same direction as the regional stress field. The principal horizontal stress direction.
From what?
Oh, from focal mechanisms, GPS, all this eastern.
All this eastern stuff has a
I
grain.
mean, the direction of regional stress.
Regional
Signal
stress.
on horizontal.
Tension. Are there any cores in the?
People started to take course, yeah.
Are
So I guess, Bob, I'm trying to figure out why would the regional stress cause these patterns of these
Well,
ponds?
I'm just making the comment, that's the
Yeah.
correlation.
Yeah,
It would be something that would have to be connected because the stress field continues with depth. So there has to be something more fundamental,
yeah.
connectivity with the basement, perhaps.
Yeah, it just seems like if there were lineaments and there was a stress field, that we would get elongate features. We wouldn't necessarily close these things off.
They're
like
not really
ovals.
in lines. They have the same orientation.
Yeah.
But they're not really in lines.
Yeah, they're not in lines, yeah. So, this is kind of puzzling, and I think for the, yeah.
I was just gonna say, this may be just too wild, but I have flown over a similar landscape in the former East Germany, where there's agricultural communities and they have just consistent circles and ovals and walls, and I just think I wonder if I would go back to, say, hunter-gatherers, maybe
Yeah.
15,000,
Catching water.
20,000 years ago.
Except these things are half a mile across.
Yeah, that is a lot of work.
Well, these
Yeah.
are large in Germany too, and hunter-gatherers had a lot of time. I mean, that's what they did.
Yeah. Well,
This is iron transfer.
oh, this means like I didn't want somebody looking it up while we're talking about it. Yeah, the students.
The one image you had of vegetation, it almost looks like there's some preferential difference in the soil type, because you had better vegetation kind of in the,
Yes,
They're
In the-
depressions.
but they're depressions, and so that's
So
where
they collect
water is
water.
accumulating, yeah, yeah. Okay, well, I'll keep going here. One of the things that Tobias said is, well, the shape of these is kind of a lot like paint droplets. And if you're painting and you splatter stuff, it tends to have these kinds of shapes of the droplets. And he said, hey, those droplet shapes are just like these. And one of the things about geologists is I think we get set in a particular mindset, and it's hard for us to change our parameters of thinking. But one of the things he said is he took all the long axes and he tried to correct for the curvature of the earth. And he noticed that there were also similar features that were here in Nebraska, eastern Nebraska. And what he did was he took all the long axes, and these are going actually all up and down the coast, not just the Rex, North Carolina. But he projected all these back, and he found that they kind of intersect right here near Saginaw Bay. And he said, I think that this is something related to an impact. And the idea was that maybe this happened in the terminal Pleistocene. You know, maybe the ice sheet was like here, maybe something hit here, and it actually caused a lot of that water to melt and actually kind of be like a wet spray that actually went out. And somebody mentioned, would it have been some kind of an angle? So if you had an impact that came in at an angle and then it kind of sprayed out in these arcs here, could that explain those ponds? And one of the ideas that he put forth is that we would call this a butterfly ejecta type of distribution. And this is an image from Mars, and this is where an impact comes in at a very low angle, like this, and it hits, and then it sprays out all this material. If it's unconsolidated and loose, it's going to make some of these, maybe some of these pockets. And maybe some of that spray actually hit the Carolina areas and made some of these elongate ponds.
if it, you showed that as being up in the, where there was a glacier. You kind of wonder what was the ejected. Was it chunks of ice?
I think that the item hit it and melted the water quickly, and then it blew it out.
Yeah, I mean, the idea is, could there also have been sand, you know, mixed in there
Yeah.
that could have sprayed out? these are things we don't really know. We weren't there. All of this is just conjecture based
It was a
on
fireball.
seeing things and not having any other viable explanation for how it would form. So this is highly controversial. People don't like to call on these kinds of things. And his idea was that there was this blanket ejecta slurry. Maybe the comet was coming in at 3,000 kilometers per hour.
In a big fireball, and it melted
Yeah,
the glacier, and it
maybe,
went
maybe.
everywhere.
What do you think
What's
of
the
that
scale
idea?
of that?
The scale? Oh, this, I'm not positive, Bob, of what the scale of this one is.
2,000 miles an hour is not that fast, really.
Yeah, that's
for,
kind of
Yeah.
slow.
For
Yeah, for
a
some
bolide.
coming in, yeah. These are just some of the things that he has put forth. And so you can imagine there's all kinds of holes
Well, it
in
wouldn't be
this.
water.
What?
I mean, it wouldn't be water, blobs of water from
Well, I
1,000 kilometers away.
think he's saying it's a slurry of a mixture of sediment that was probably
Then
in
you
with
should be
it.
able to find different sediments there.
Possibly, and that's not something that has actually happened yet. So the whole idea, though, what I think is interesting is that we have focused on these things: climate, sea level, and tectonics. Those are the three things that all the textbooks say. That's what explains the sedimentary record. And yet, one of the things that we don't think about that much is what about impacts? And we're often looking for, we got to have a smoking gun. The reason why geologists don't want to jump on this bandwagon is because they don't find the smoking gun. So what is a smoking gun? Well, it's kind of interesting to look at the distribution of impact structures on Earth. We have like maybe 160 of them. Here's where they're kind of distributed. And of course we know that on Earth we've got plate tectonics. Water is covering almost 2/3 of the planet. And so probably only young impact craters are going to be very well preserved. So we don't have that many on Earth. But it is striking when you compare Earth with, say, Mars. This is a projection of Mars. It's flattened out. But, you look at all these craters that are greater than 4 kilometers. And wow, okay, Mars has a thinner atmosphere. And so, more meteorites would get through, etc. But it is really striking, the difference between Earth and what are documented impacts and a planet like Mars.
Your Earth one has got to be almost recent, or
They
can
have
be
to-
seen at the surface.
They have to be
because
relatively young.
There's a ton more in the subsurface.
Probably, yeah.
There's
So,
some very big old ones, of course, that are.
Yeah, there's a few old ones that are on the craton. But, these kinds of features are very visible on Mars. And on Earth, if we have something like Meteor Crater, okay, we'll say, yes, that is a meteorite impact. We have the nice crater shape. And, of course, we have meteorite material. And so we have simple craters like this that have this simple geometry. We can also have complex craters like this. And these will have a central uplift. And even some craters, some features like a pupal dome, have been argued about for a couple of decades now. Is this a complex crater because it has this central uplift part? Well, this is kind of some of the...
Is the center of that image salt? Is that a salt dome?
This is controversial. Is there salt at depth? The actual material that's in here is a little bit of Permian white room sandstone and some of the Moenkopi and some of the overlying chinle is right down here towards the bottom.
If you go back one image, when I commented about there's a ton in the subsurface, and just for an example, this was a very deep groove in my brain since I just hired on with Exxon, and there'd been a discovery in the Williston Basin. Now,
Red Wing Crater.
Right. If you're familiar with Williston Basin, it's this gigantic circular basin. It goes from Canada to Montana and covers most of the Dakotas. Well, True Energy decided to drill a well right in the middle of it. They get down and they find this monstrous oil field, or very thick Mississippian pay. It's full of oil. You go 3 or 4 miles in any direction, and through all the rest of the Williston Basin, the Mississippi Mission Canyon is about 400 feet thick, 300 to 400 feet thick. Where they drilled that well, it was 750 feet thick. And the only thing we could conclude is it was an impact like your lower image there, where it came in and just completely shattered the limestone, and essentially you had a much thicker accumulation. The other comment I'd make is, if you back on your images of impacts around the world, if you think about what happened in Yucatan, we know the big right. The biggest field in Mexico is Campeche, which is
Cantarell.
and it's the Cantarell field, which is a brecciated carbonate right on the side of that where that meteor must have hit. That is the where all the oil is in that field.
Yeah. Well, I mean, I just think that this is raising the point that we should be thinking more about this than we have in the record. So let me just kind of quickly go through some other ideas of the smoking gun. People have said you got to have this meteoritic material, and if you have that, okay, nobody's going to argue with you. Shocked quartz is the other thing that we're often looking for. If we have these planar deformation lamellae, and we're saying that if there is a big impact, there's a shock wave that actually makes defects and displaces some of the crystal structure in some of the quartz grains. So this is something else people would look for. Other things that people would look for are shatter cones. These types of cones that kind of spray out that they think is related to the radiating point of an impact. And the energy is deforming the rock. Sometimes these tectites, which are almost kind of like obsidian, you get some of these great examples from China, and these are probably from molten glass that forms from the impact. Spherules, they almost kind of look like ooids, but these are glassy spherules that seem to form in a layer, probably that came out of a vapor plume when you had this impact. And then some of the ideas of even big breccias. This is a huge breccia that's called the Devonian Alamo breccia from southern Nevada. And for a long time this had been interpreted as a tectonic detachment zone. But people have now decided that this was an impact that hit a carbonate shelf, broke up these breccia pieces. You can see things like calcitic type of spherules, and there's other evidence that people think are more of the smoking gun to make the interpretation that this is a record of an impact. And probably one of the best known impacts that we just had the opportunity to see last year is Reese Crater in Germany. This is one of the best preserved impacts. It's been mapped out very carefully. You can see the concentric nature of this. They have a lot of high pressure minerals that they know are not from volcanism. So they've got impact diamonds, stishovite, and coesite. Those are shown examples here. And the impact happened about 15 million years ago. They can see these nice examples of shatter cones, and they can even see these blast striations where they think material was actually kind of made grooves as it scraped across the bedrock when this impact happened. So here's the idea of the Reese Crater. There was a big impact here. There were breccias that were laid down, and then afterwards, after most of the big pieces were laid down, there was this cloud of broken glassy material. They call this a swayite that actually covered a lot of this area here. And the swayite is a very distinctive rock, even though it can look a lot like a volcanic rock. But they find the swayite in some of these areas, surrounding areas. These are some of the bigger blast orientations that they can see on some of the Jurassic limestone. So where they're actually quarrying, they can see some of these. And I asked my husband here to align with the striations. And you can see the striations that are going like this, where material just came right across the surface and really kind of made that groove. And here's the swayite. You see this breccia that was related to the impact, and then there was this melt rock, this swayite that's up on top. And they actually had made the church in Nordlingen out of this swayite material. Very best swayite was made for the church, but what's happened over time is it's degraded because glass is unstable. And now they're actually having to replace some of the rock with other types of stone because there's no more high quality swayite that's left. But this is what the swayite actually looks like. So I want to show one picture of things that are helping us understand impacts more. And these are experiments. So one of my colleagues has a sandbox. He has a gun that he shoots at this. And then what happens is you can actually model the impact. Look at the size of the crater diameter relative to the impact velocity. Look at this blanket that gets laid down. And it's some of these kinds of experiments that are being done now to help us better understand impacts and maybe even what the material is and how they would form. So impact experiments are going on. You know, the idea of impacts is not really new, and almost 2 decades ago, a U.S. Geological Survey geologist had all these maps from around the world, and he had drawn circles around anything where he saw an arc. And so he was kind of presenting this, and a lot of people just thought this was totally ridiculous and ignored him. I think probably there's something in between what he had come up with, but he even tried to put Gondwanaland back together and see if some of these arcs actually matched up. So, you know, what caused the extinction of the dinosaurs? You know, a lot of times we're using circumstantial evidence. Well, yeah, was this a smoking gun? Who knows? But these are interesting ideas. And I think, you know, what I've tried to do is give you a sampling of some sedimentary hot topics. I think probably impacts are more important in the stratigraphic record than we've given them credit for. And I think really we need to change our textbooks, and that the next generation needs to be thinking more about that. Not necessarily that they'll jump to wild conclusions, but right now people aren't even really thinking about that when they go out and look at a sedimentary section for the first time. So there's still lots of mysteries, and these were just a couple examples. The last thing was, you know, about new paradigms, and even the way we are getting information is totally different. You know, this was our old way of getting information. And what's happened is that now we're all doing this. I don't even go to the library anymore. And it's a little bit embarrassing, but the way people find information is totally different. And, you know, there have been lots of things that have really changed our lives in ways that it's hard to imagine going back to doing it the old way. And I mentioned that one of the things about EarthCube, this idea of using cyber infrastructure, is that we want to be able to have all this information at our fingertips. And so we want to be able to go to a spot and say, you know, what's the information there? You can look at quartz maps. You might be able to hone into a particular area, pull up the geologic map, actually go into further detail, pull up another map at a higher resolution scale, maybe actually say I want a cross-section of this area, be able to find all that information just by these little clicks, or really honing in on even a spot. And you would be able to pull up the stratigraphic section, maybe even get pictures of the outcrops, maybe even find out who had taken samples at a particular outcrop, what was the actual reference of that material, and maybe what were some of the actual analyses that they did.
Wow.
So those are things that I think are on the horizon for the future. And I think that my own field of sedimentary geology is really one of the slowest to come around to what we need to do. And so I wrote this article that the future of field geology and all this open data sharing and cyber technology has to happen. And if the sedimentary geologists do not get on board, what's going to happen is that the train is going to leave the station without us. And I think that that's a real scary thing. We really have to be on board, because if people try to force a certain system on us and it doesn't work with our workflow, then we're not going to use it, and then we're going to be left out. So one of the things that's coming soon is a field application. It'll essentially be some kind of application where we can record all the things that we normally would have written in our field notebooks. And already the structural geologists are way on top of things. They've already developed a prototype of a program that they call Strabo, that's specifically for structural geology. And just recently, I've gotten a grant from NSF to add the sedimentary component onto the existing Strabo. So this is a little bit like a spot thing. And spots can be anything from an outcrop to a particular spot all the way down to like an individual, you know, millimeter type of spot. And this is something that's fairly effective so far and going to change thinks in the future. So I'm trying to get the sedimentary geologists worked up about this, using this platform. I also wanted to briefly mention that there is the program that's been developed called Macrostrap. This has been developed by the University of Wisconsin, where they took all of the major maps at core scales, and they took all the former continental drilling project data, and they've all integrated that into a database, and that's called this Macrostrap. And they've now developed, so they have over 1,000 regional rock columns. They've got over 33,000 rock units. They've got over 1 million map polygons, geologic map polygons. And the idea is to make a database that people can actually use. And one of the programs that he has that I think people might find interesting is this one that's called Rocked with a D at the end. And this is one where you can download it for free if you have like an iPhone. And then what you can do is you can be at any spot, and as long as you have the GPS capability on your iPad or your iPhone, that type of thing, it can actually tell you what is the geology right at that spot that you're at. And it'll pull up a stratigraphic column, and it can also give you the geologic maps. And so this is kind of the wave of the future. It's not perfect because it, again, is based on the continental drilling data. And if you're, at a spot that's far away from where the actual columns were, it might not be exactly right. But it is going to be handy. Another one that was developed is called Mancos. It's called Your Geology Right Now. And again, you just want to know where you are based on your locality and pull up the geologic map that'll tell you what unit it is. This is one, I think it's about $5 that can be downloaded.
Does any of that integrate directly with Google Earth?
These won't. These use some Google Earth type platforms, but most of it is not Google Earth because Google Earth said we don't want to partner doing that kind of stuff. We've got our own business model. So it's kind of unfortunate because it would be logical to use the Google Earth. But
By the way, we've been trying to incorporate Google Earth into our similar type applications, and they just don't want to cooperate. If they do, they want a lot of money for it. So we've gone to Open Mapping, which is a new tool which you can get, and it's free downloadable. It's the equivalent to Google Earth, and we're using it.
yeah, and I think that that's probably what some of you are using. Both of these, the RockD and then the Mancos, both of these are based on the Macrostrap data set. But it's just an application that's specifically to try to tell you the geology right where you are. So I think, the bottom line is that the future has got a lot of interesting things on the horizon. There's going to be a lot of this cyber infrastructure that will change the way we do geology as well as the way we get information. So that's my story for today. Thank you.
Let's the other one. That
This
one.
one?
Bingo.
Okay.
Questions?
That's great. Is that Earth Cube available to the public?